Okay, so we are in weight initialization. Why do we need to initialize weights properly? Because if we don't initialize weights properly, vanishing gradient will happen. What is vanishing gradient? When we try to update weights, dou L by dou W, this is called a gradient, and gradients become so small that weights don't update. That is the issue. So before learning how to initialize weights properly, let's learn how not to initialize. Sections are already told that randomly initializations is actually correct, but initializing from very small variance or large variance will lead to some issues, like vanishing gradient and exploding gradient in ReLU. So these are few issues. So first learn what happens when we initialize with small variance. What is small variance actually? So usually in the universe, normal distribution is extremely so common. So we take normal distribution. So we have a normal distribution with a lot of points in it. All these points now, the mean of these points is 0, and the variance is extremely small, like 0.0001. So this is so small that any point you take, it's going to be very close to 0. So all these weights now, this W11, W21, and any weight here, this, all these weights are going to be extremely small and close to 0. So what happens when we take such small values? Okay, well, let's take a simple neural network. It has two inputs, x1 and x2, and has four neurons in the hidden layer and one output neuron. Sorry. X1 and x2 are already normalized or standardized, so the values of x1 x2 are going to be small. They are probably going to lie between -1 and 1, or 0 or 1. So no issue from that. And we know that W11, W21 are very small. Now let's calculate the Z1 value. Z1, we know X1 is small, W11 is so small, it is close to 0. So the multiplication of this is also going to be very small. Similar is the case with X2. X2 is small, W21 is so small, it's close to 0. So multiplication of these two is also going to be a small value. And when we add two small values, that is also going to be very small value and close to 0. So Z1 is close to 0. We have an activation function sigmoid. For case 1, let's assume we are using sigmoid as activation function. Sigmoid as activation function. Okay, let's use sigmoid. So sigmoid, when we give it 0, the output is 0.5. So since this is very close to 0, the value of f of z1 is going to be close to 0.5 and not exactly 0.5. It is close to 0.5. Okay, so here O1 is going to be 0.5. Let me write it. O1 equal to 0.5. So since O1 is 0.5 now, x1 x2 won't change. Likewise, for other neurons also, same thing is going to happen, same thing is going to repeat. All the outputs from this neuron, the output from this neuron, output from this neuron, all are going to be small. And we have initialized these weights are also, and they are also very small. So the aggregated sum of all these weights and outputs is Z2, that is also going to be very small value, and it is close to 0. So what is O2? O2 if f of Z2 equal to sigmoid of 0. So it's going to be close to 0.5. So what is this issue? Why, if it's 0.5, what is the issue? In backpropagation, let's say we want to update this value W11. Okay, so how do you do that? We have this W dou L by dou W11. Using chain rule of differentiation, we can write it in this form. How does it come? Because loss depends on O2, O2 depends on Z2, Z2 depends on O1, O1 depends on Z1, and Z1 depends on W11. So because of this chain relationship, we can write this dou L by dou W11 in the same order. See, dou L by dou O2, O2 by Z2, and this Z2 by O1. Okay, and here O1 by Z1, O1 by Z1. Okay, this is Z1 by W11, Z1 by W11. We can write like this. Now, if you look into this equation, this dou O2 by dou Z2, this is basically, we can write O2 as sigmoid of Z2 na? And also this O1 we can write it as sigmoid of Z1 na? Okay, so what is this here? Basically we want the derivative of sigmoid, and we know that the derivative of sigmoid at value x equal to 0 is 0.5. So when the value is close to 0, the derivative is going to be close to 0.25. Okay? So this value is going to be close to 0.25. This value is going to be close to 0.25. Already these values are small. And you are multiplying with a fractional value, then it is going to be very small. Imagine this is a small simple neural network which only has one hidden layer. As we go on increasing the number of hidden layers, this chain is going to be so long, and the number of 0.5 terms will also increase. And what will happen? This gradient is going to become extremely small. When it becomes extremely small, we know now what is this, new weight equals to old weight minus learning rate into dou L by dou W weight. We already know this learning rate is small. Again, if we make this small, the multiplication of these two is going to be even smaller. It's so small, it is going to be close to 0, and the weights won't apply, and our neural network will not learn. That is the issue. This is called vanishing gradient. So this is the case with sigmoid. What if we take tan h then? In tan h, at 0, the values are 0, and the derivative is close to 1. In sigmoid it is close to 0.25. In tan h it is close to 1. So even though it is close to 1, we will still have vanishing gradient. Why it won't disappear? Because there are other small values, and also anything you multiply with a fractional value, the value is going to decrease further. So because of that mathematical reason, we will still have, but not as much as sigmoid. Okay, so why not? Then the other option is ReLU. So in ReLU, while using ReLU, the derivative of ReLU is exactly equals to 1. So here also vanishing gradient can happen, but not as much as tan h or sigmoid. Less chance. But there is another issue called this dying ReLU issue, because if you get any value less than 0, so the gradient is going to be 0, and the entire this entire term is going to be equal to 0, and weights won't update. So this is vanishing gradient for you, and this is what happens when you use small variance. So let's take large variance. Okay, let's take extremely large variance. We have a normal and we have extremely large variance. Let us assume 1 million variance. So this is going to be minus 1 million. Let's say this is minus 1 million and this 1 million, and these values are so big, very huge, huge values. So what will happen when we use huge values? So same ANN, same neural network, sorry I forgot one neuron here. Same thing here. What happens? Let's see. Let's send two inputs x1 and x2. Those are normalized, those are normal values, no issue. But these weights are the real trouble. They are very huge. So these values lie between 0 and 1, and these values are in the magnitudes of 1 million. Okay, so when we have such a huge value na, the entire aggregation z1 is going to be very large, and sigmoid of any large value, what is it? Sigmoid of any large value, it is close to 1, and sigmoid of any large value is close to 0. If you leave that, when it comes to this term, here we need to get the derivative of it, derivative of sigmoid. Let's look at what is the derivative of sigmoid. Okay, here the derivative of sigmoid for extremely large negative value or extremely large positive value is close to 0. It is very tiny. This red one is there na, that indicates the derivative line. So for large values na, it is tiny and approximately equal to 0. When it becomes 0, what will happen? You multiply this entire thing with 0, it will become 0, and no weight updates happen, and again vanishing gradient. Same is the case with tan h also. In tan h also, this is the derivative level. For extremely large values, the derivative is becoming 0. So it is so close to 0, the weight updates won't happen. And but what happens in case of ReLU? Okay, in case of ReLU, if it is a negative value, then the derivative is exactly 0, and the entire thing will become 0, and the output becomes 0, or neuron will die. But if it is a positive value, see, look at this is growing straight. So for extremely large value, it's going to be very large value, and the weight updates will take really long, and the gradients will be so large that weight update will take really long. This is called exploding gradient. Oof.